Lesson 2. Launch, explore, discuss. Please be discreet. The first discrete is the kind of discrete where you make good decisions. The second discrete is the mathematical term. In the jumpstart, we're asked which one doesn't belong. And really, the answer is any of them. You just have to give the reason. These numbers are all different. Here's how. Let's take a look at this diagram. Have you ever seen this before? Numbers like 1, 2, and 3 are called the natural numbers. In fact, sometimes 0 is not considered natural, it's considered a whole number. Natural is called that because that's the way you first started to learn how to count. Then when you add negatives to those, you get what's called the integers. So a natural number is an integer. It's inside of the integers. Then you have fractions, and you were introduced to fractions, decimals. Those are numbers that have the ability to be written as fractions. Integers can be written as fractions. Natural numbers can be written as fractions. Then you have what in this diagram is called real algebraic, or some people call these the irrational numbers. In fact, it says irrational right here. These are numbers that can't be written as fractions. And then you have real numbers. Now, remember, a natural number is a real number. But real numbers include things that cannot be written as fractions. It's kind of like the fact that Ontario is inside of California. So when you're in Ontario, you're in California and you're in Ontario. How can you be two places at once? Because one is inside of the other. So how can a number be more than one thing at once? This is how. Now, coming back to here, 2 is a natural number. -2 is an integer. And the symbol that we're going to use for integer is Z. C is a rational number. We're going to call that Q. The square root of 2 is irrational. Now, we don't give a specific symbol for that, but we'll come back to it in a second. 2.22 is a rational number, but it is also a repeating decimal. Believe it or not, you can write repeating decimals as fractions. So irrational numbers are sometimes called real numbers without the rationals. Every number here has something about it that's unique. Now, in these problems, we're asked to basically do what's called the rule of 4. The first is word problem. Okay, these are given to us as a word problem. The next is make a table. The next is make an equation. The next is make a graph. So Library of Congress is the biggest library in the world, some people think. And they have books that are shipped there. The books can be heavy. They aren't shipped in big boxes. They're shipped in littler boxes, and each box contains about 8 books. That's a key piece of information. How many books are received by the library in 6 boxes, 10 boxes, N boxes, etc. So what we would do here is we would think, okay, well, I'm multiplying each box times 8 because of this number. So the equation could be something like f of n equals 8n. The domain meaning what kind of numbers could we use? We could use the whole numbers. We could use 0, 1, 2, 3, 4, 5. If you wanted to say natural, that would be okay at this point. A table of that might look like 0 boxes, 1 box, 2 box, 3 box. No books, 8 books, 16 books, 24 books, etc. A graph of that. I'm not going to go into great detail on the graph, but basically, you depending on your scale, you could say that, let's see, how about there's 8, and then we could do it again, and we could do it again, we could do it again. The point is, we're not going to connect these dots together because it wouldn't make sense to have an in-between number of boxes. It wouldn't make sense to have half a box or 2 boxes and a half or 2 boxes and a quarter or any kind of fraction or anything in between the whole numbers. So we're going to call that later on, we're going to call that discrete. Okay, number 2, many of the books are electronic. About 13 ebooks can be downloaded onto the computer each hour. If about 13 can be downloaded each hour, how many ebooks can be added in 3 hours, 5 hours, etc.? That one is going to be continuous. I'm going to use X instead of N. So you're going to find this as you go throughout mathematics, that usually N, this is a key hint here, N is usually used for discrete situations where it doesn't make sense to look at the in-betweens. X is going to be used for continuous situations. At least this is my experience. The domain could be any number that's positive. A table, looking at that, would look like 0 minutes, 1 minute, 2 minutes, 3 minutes. No books, 13 books, 26 books. Oh, I guess those are hours, not minutes. 39. The key difference in the graph, though, is that this one would be solid. Okay, I didn't take a whole lot of time with the graph, but if you go to desmos.com and you type in f of x equals 13x, you'll see exactly what the graph is supposed to look like. Okay, librarians are working to put the books on the shelf. A librarian can sort and shelve about 3 books a minute. 3 books a minute. Okay, well, what would that look like? Would it make sense to go 1/2 a minute or 45 seconds? Sure it would. And so we're going to use X on this one. If we do 3 books a minute, that's 180 books an hour. So if we did this, then X would be the number of hours. And the domain would be any positive number. The table, 0, 1, 8, let's see, 1, let's see, not going to do 180 there. We're going to do 180 on the other side. 1, 2, 3, this would be 0, 180, 360, 540, and so on. And again, the key point here is in the graph, you want to see the graph, go to Desmos, but it's going to be a solid graph on this one as well. Then question number 4 is asking us, would it make sense for there to be a time when 32.5 books had been shipped? And I would say yes, on the electronic downloads, because let's say in the middle of a download on your 30-second book, let's say the power went out, then you would only have a half a book downloaded. Otherwise, you're going to get a whole book when you're getting it in a box. Okay, 5, which of these situations represent a discrete function and which represent a continuous function? The ones with dots, those are discrete. This is discrete, number 1. The ones with a solid line, they're continuous. So 1 was discrete, and 2 and 3 were continuous. Okay, now we're going to cut a big piece of paper and think about how many sections that would put everything into. Using a table and a graph and an equation. How many papers after so many cuts? So you would have to look at and start counting that you have one piece, and then you have 1, 2, 3, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we went 1, 3, and 9. Sound arithmetic or geometric to you? Well, it sounds geometric to me. It sounds like we're multiplying by 3 each time. So how many papers after a certain amount of time? Okay, so our equation would be f of n is 3 to the n, and our table would look like 0, 1, 2, 3, and then 1 piece of paper, 3, 9, and 27, and so on. We're multiplying by 3. Our graph is going to be just dots. And the reason is, and I'm not going to make this very accurate, okay? The reason is, it wouldn't make sense to have fractional cuts. It wouldn't make sense to have a decimal cut. Only whole number cuts. But it is growing very fast, exponentially, we'd say, in a curve. So what is the domain? These are whole numbers. Wouldn't make sense to have 5.2 cuts because they must be whole numbers. We just said that. Would it make sense for the part D? Would it make sense to look for the number of cuts it takes to make 53.6 papers? Again, no, because you can't have partial papers. No partial papers. That's why this is discrete. Now, medicine taken by a patient breaks down in their bloodstream and dissipates. That means it goes away. With the work of the kidneys, the work of the liver. And suppose we start with 60 milligrams of a medicine given to a dog, and the medicine breaks down, so 20% of the medicine becomes ineffective every hour. That helps us to do our equation. If 20% leaves, 80% stays. So is it continuous? Yes, it is, because it makes sense to think about in between the hours. So f of x is, it's going to start at 60. It's going to go 0.8 to the x. On a table, that would go 0, 1, 2, 3. That would look like 60, and then 80% of that is 48. 80% of that is 38.4. 80% of that is 30.7. What it's going to look like on a graph is smooth curve coming down. It's going to start at 60, wherever that is, and it's going to come down like this. In the mathematical model, you're never going to get rid of all of it. But in reality, we know we are. The domain of the function is positive numbers. Would it make sense to look for an amount of active medicine at 3.8 hours? Yes, actually it would, because the change is continuous. Continuous change. Would it make sense to look for when there is 35 milligrams of medicine? Basically, it's the same answer. Yes, because of continuous change. Which of the following functions, or which of the functions modeled in problems 6 and 7 are discrete and which are continuous? So 6 was discrete and 7 was continuous. What needs to be considered when looking at a situation or context to decide if it fits best with discrete or continuous model? And one of the things you can look at is, do you have discrete or continuous inputs and outputs? Inputs or outputs. Describe the differences in each representation for discrete and continuous functions. We're going to get to that in a second. Which of the functions modeled in the task are linear, which are exponential? 1, 2, and 3 were linear, and 6 and 7 were exponential. Let's go down to our takeaways section. In our box here, when you have discrete, then the change happens instantly. When you have continuous, the change happens gradually. So in the tables, all whole numbers. In continuous, some fractions or decimals could be possible. In the graphs, you're going to have dots. In the continuous, you're going to have lines or curves. Equations, you're going to have f of n, you're going to have n. In continuous, you're going to have f of x, you're going to have x. In your domains, you're going to have whole or natural. In your continuous, you're going to have real numbers. Okay. Now, for set builder notation, we're going to skip this part for now. Okay? We're going to end right here without doing the retrieval. To answer question number 10, just look at our takeaways section. We'll see you next time.